Hello and welcome to a review of exponential and logarithm functions. Here we have before us a couple of questions that are multiple choice and ask us to sketch the graph of each function. Of course, since it's multiple choice, we are going to be able to use some process of elimination that we wouldn't be able to use if we were actually having to graph this by hand. So I want to draw your attention to the kind of parts of these functions. These are exponential functions, and on number 1, your base exponential function is the 2 to the x, and so that means that we have exponential growth. That means that this -2 in the exponent is a shift right of 2. This -2 on the outside is telling us that we are shifting down 2. These transformation rules, if you don't know them, they'd be super helpful for you to learn, and I plan to actually do a video specifically on exponential functions very soon, so if I get that up, there will be a link in the description for that. So we are going right 2 and down 2, but this -3 in front means that we are reflecting across the y-axis as well as vertically stretching by 3. So the fact that all of this is happening at once and it's an exponential function makes me personally sad, because it's a lot of things to think about. I can start eliminating things though by saying, well, b is what it would look like if it wasn't reflected across the y-axis. In general, I don't actually know if any of the numbers are correct. I just know that this one does not fit our model of reflecting across the y-axis. And then we could actually think about this down 2 part at least, and maybe the left 2 part. Down 2 means that instead of our asymptote for exponential functions, which is normally at y equals 0, we should be at y equals -2. So that's this one fits that, this one fits that, this one does not. So now we have a 50-50 chance. And either before this or now, one of the things we would be able to do is plug in numbers to see if we can find points that match up. And instead of picking a 0, which would give me a negative exponent, or 1, which would still give me a negative exponent, I personally would pick to try 2, so that I can do 2 minus 2, which is 0, because 2 to the 0 is 1, and then -3 times 1 is -3, -3 minus 2 is -5, so that means that when I plug in 2, I get -5, do either of these, and hopefully not both, have the point 2 comma -5. 2, -5. Wait. I mean, that's not where -5 is. -5 is up here. Because my scale is by 2. So 2, -5. Yes, this one has it. So it is C, not A. So that's kind of the process we can go through to try to narrow down our choices. And sometimes it'll be easier than others. Like, for instance, the negative there only got rid of one of our choices on the first one, but this one actually is a positive in front, which means, and since it's a base of 3, that means this should actually go up to the right and even out to the left, like good old exponential growth that we know and love. And there's actually only one choice that does that. So if you can know something about how the functions work, that can really help you eliminate choices. But if you don't know enough about how the functions work, or if you start to doubt yourself or anything like that, then making a table of values is always a great option. You should go for it. That's better than nothing. And if we're not given multiple choice, which often we aren't, then a table of values can be really helpful to help you graph. So let's give that a try probably on this next problem. So here you see we have a graphing problem, but this time it's not multiple choice. We have a base here of 3, and we have 2 transformations happening here. This +2 is part of the super secret opposite society, so that means we're going left 2. The +2 out here is not part of the super secret opposite society and is telling us our up and down, so we're going up 2. Now the transformations only matter if you know what 3 to the x should look like, and if you don't know off the top of your head, it's pretty easy to figure out. right? Because when you plug in 0, you get 1. When you plug in 1, you get 3. Well, that's what we are transforming here. So instead of it being at 0, 1, we need to go left 2 and up 2 to right here. Instead of it being at 1, 3, where it normally is, we need to go left 2 and up 2. And I also personally think it's really helpful to know where the asymptote is. Normally our asymptote is at y equals 0. And so left 2 doesn't make a difference there, but the up 2 is going to make it be at y equals 2. So we are going to go this way towards our asymptote, and then we're going to go this way away from our asymptote. And that is our exponential graph. Now number 4 changes the game on us. We've got logarithms. And the problem with logarithms is we are less likely to be able to just plug in numbers willy-nilly, because you have to be able to make a connection between the base 6 and what's inside here being a power of 6. That's not to say you can't do it, but this is usually where having something memorized makes it easier. For instance, a normal logarithm with a generic base of b goes through the points 1, 0, the base, 1, and its asymptote is a vertical line through x equals 0. And the important thing here in the middle, that whatever your base is, that is where your next x point is going to be. That is a nice x point. So this is plus 5 inside, so that's a shift left of 5. Plus 5 on the outside is a shift up of 5. So normally for log base 6 we'd graph 1, 0, but we're going to move it to the left 5 and up 5 to right here. And then our next normal point for log base 6 would be 6, 1, because it's the base, 1. So we need to take that and move it to the left 5 and up 5. And then our asymptote is normally at x equals 0, but we're going to move that to the left 5. It's a vertical asymptote. And logarithmic functions are weird looking in my opinion, because yeah, it's just if you reflect an exponential curve over a diagonal line, but I don't know, something about it just always looks weird. You want to just kind of swoop over to the right, and then you want your graph to take a real nosedive toward the asymptote. And the curviness of my graph toward the asymptote is because drawing it on a computer is hard. It's not actually supposed to be curvy. It's supposed to go smoothly towards the asymptote on the left. But you know what? At least I showed you that it went down to the left, because your calculator is lame and doesn't even really show you that. So take that, calculator. Alright, using our powers of process of elimination as well as what we know about graphing logarithms, this should be easy peasy. We have a shift left of 5 here and a shift up of 2. And so I think here what's going to matter is where our asymptote is. Normally it's at 0, but we're shifting it left 5, so our asymptote should be at -5. This looks like it's getting really close to -5, and in fact, when like a computer or a person is graphing, often it will look like it gets to -5, because people are not perfect. But it definitely looks a lot better than C or B. I just realized D also looks like it has the right asymptote. So next plan. One way to do this, to decide between A and D, is to think which one of these looks more like it's been moved up to, which since D is higher, I feel like that suggests up to. We also could go ahead and try to use one of our points, like 1, 0, we need to move left 5 and up 2, and oh, that puts us right here. Keeping in mind the scale here is by 2s, so you have to be careful with that. But that does look like it matches up, whereas A would not match up. So that should be our answer. Look at the nice swoop here. This is what a logarithmic curve should look like. So if you were looking at my curve on number 4 and thinking, has she even ever seen a logarithmic graph? What is this? That is exactly what I meant to look like, is what these graphs look like. It's the same, of course. Number 6, y equals ln of x minus 1 plus 2. Now, ln is fancy talk for a logarithm with a base of e, and it's called the natural logarithm, but in a language that switches things around, so that's why the L is first and the N is second. And so that just means that our base is something that is kind of close-ish to 3, but not so close to 3 that we just like round it to 3. So if you don't know anything about E, it's like 2.7 something something something. It's a button on your calculator. It's kind of like pi, where it's a number that goes on forever. It has significance in math and all that jazz. So the minus 1 inside is telling us to go right 1. The plus 2 on the outside is telling us to go up 2. That means that our asymptote is not at x equals 0, but is at x equals 1. Does that help us out here? Could be this one, could not be this one, could be this one, could not be this one. So that helped. We're supposed to be going up 2 again, so probably not this one, but I like to actually pick out a point just in case. Normally it's at 1, 0. The fact that this has a point at 1, 0 is not actually good enough at the moment. I'm going to take 1, 0 and move it right 1 and up 2. There we go. That is actually a coincidence that that first point I drew was on there. It did not have to be like on there. Like, I don't know. That's a coincidence that it was on there, I think. So A is a good answer here for us. Alright, we are using properties of logarithms now to first expand and then condense. So when we expand, we are taking one logarithm and writing it out so there's more than one logarithm. We're making it longer, which is usually the exact opposite of what we're trying to do in math. Now, the way we do this with expanding and condensing is when you have more than one thing inside of a logarithm, if they're being separated by division, like in number 7, you can separate it into 2 logarithms with subtraction. If they're being put together with multiplication, like number 8, then you can separate them and you put addition in between. So there's a connection between subtraction and division, addition and multiplication. So our first step on expanding number 7 is going to be to write it as ln of 11 to the 6th minus, because we're dividing, and then ln 7 to the 6th. But that's not all. We also, when we are expanding, typically will take the exponents and move them. So there's this super cool property about logarithms that having an exponent here is the same as if you were to write it with that number in front and not have an exponent anymore. It's actually like a super handy thing that you can use later on in math to great effect. This should be the answer to the expanded form of this logarithm. In a similar way, we're going to expand number 8. This time our base is 7, so nothing is going to change the base when we're expanding or condensing, and if things didn't have the same base, we wouldn't be able to condense them into one thing. They have to match bases for this property, for these properties to work. So we've got W, and then we've got square root of U times square root of V. So a couple things here. For one, square root of U times square root of V can just be separated into 2 separate square roots. But also, isn't there like an exponent or something that goes with square root? Isn't it like U to the like 1/2 is the same as the square root of U? Yes, it is. So what that means is we are going to be able to expand this by saying, okay, we've got W. We're going to put plus in between because these W, square root of U, and square root of V are being multiplied together, not divided. So this is going to be log base 7 of square root of U, or if we would prefer to think of it that way, U to the 1/2. And then the same thing here can be done with V, that it's log base 7 V to the 1/2. But it switched from multiplication to addition when we separated them into different logarithms. Now I'm going to take these 1/2s and move them in front. So I've got log base 7 of w plus 1/2 log base 7 of u plus 1/2 log base 7 of v. And that's my answer. And if you are able to do that all in one step, I would say go for it. Just don't forget about doing that last step of moving the exponent. Now let's condense. So we're doing the exact opposite. We have more than one logarithm. We're trying to write it as a single logarithm. So we have to do the steps in the opposite way. These numbers in front are going to have to move and be exponents before we condense these into one logarithm. So, and again, you could probably do some of this more quickly in your head. Like you might be able to just go straight to the answer, and that's fine. So the 20 moves over here to the 10, the 5 moves over here to the 3, and then they are both base 9 logarithms, so we can combine this into log base 9 with 10 to the 20 times 3 to the 5th. Now that 10 to the 20 suggests to me that we are not supposed to actually work this out because that's a really big number. And it said express it as a single logarithm. It didn't say anything about simplifying if possible, so we'll just leave it be. Now this is interesting on number 10. We've got log base 3 of x over 3, and you might be thinking, oh yeah, division. That means I'm going to switch it to subtraction, right? But no, that is not right. We are trying to condense these, so we would move the 2 back here to where z is, so that it is z squared. But this here is actually the same as saying 1/3 in front of log base 3 of x. It actually kind of annoys me that this program writes it with the 3 on bottom instead of writing a 1/3 in front, because it kind of feels like it's trying to trick you on purpose. That 1/3 is just going to turn into our exponent, so that we have log base 3 of x to the 1/3. Now we can take these, since they're both log base 3, and put them together. Since it's a plus in the middle, we're going to put it as multiplication. And we actually can do that without even putting a dot in between, or you can put a dot if you want. It is up to you. Neither of these had a minus sign. If they had a minus sign, instead of putting it as multiplication, we would put division. So that would be a different situation than what we had here on 9 or 10. Alright, let's evaluate these expressions, and I'm kind of surprised that there isn't the added instruction of without a calculator. Perhaps your teacher just isn't going to let you use a calculator on any of this test. Sometimes teachers will go ahead and make a test of this nature, part with calculator, part without, because it is important to test your understanding of what a logarithm is. A logarithm is a way to relate a base with a result where your answer is the exponent. I don't feel like that made a lot of sense, so let me explain it a different way. The answer to log base 3 of 27 is the answer to the question, 3 to what power is 27? So if you can answer that question, 3 to what power is 27, then you know the answer to log base 3 of 27. That's the connection between these numbers, is what is the exponent that we would need to get from the little number to the big number. So 3 to the 3rd power is 27, so our answer is 3. Now, if it was just that easy, then, you know, people would like logarithms more than they do, but we also have other things that end up happening, like the fact that if I look at fractions, I could have a negative exponent involved, or we could talk about having a square root or a cubed root or things like that. Let me say it a different way. Like, if you have 2 to the negative 1st power, that is 1/2. Or if you have 4 to the 1/2 power, that's 2. We're going to use those skills as we're going along here. So log base 4 of 1 over 16 is asking us 4 to what power is 1 over 16. So we got to think about this in a couple ways. It's a fraction on this side, and it's not on the left, so there must be a negative involved. And then we think, well, what exponent would get us from 4 to 16? 4 squared is 16. So the combination of things we need here is we need a negative, and we also need a 2. So think through that. 4 to the negative 2, you would make it be 1 over 4 squared, and then you'd square it and get 1 over 16. So the answer here is negative 2. 13. What power do you raise 16 to so that you get 2? If we're taking a bigger number and getting a smaller number, but not a smaller number as in a fraction, then we've got to have some sort of power going on. Now, the square root of 16 is not 2, the square root of 16 is 4. And I can't cube root 16, but I can fourth root 16 and say that the fourth root of 16 is 2. Okay, what we need here is a fourth root. The way that roots work is that's the bottom number of your fractional exponent up here. So what we need is 16 to the 1/4 power. So our answer here is 1/4. That one's kind of tricky because it's not even like an obvious one like a square root. It's actually a fourth root, so you had to really pay attention there. Number 4 is a trick question because I should have given you more time to think about it before I told you that. So maybe now that you know it's a trick question, maybe you can figure out why if you haven't already. I'll give you a moment. So if you're thinking 5 to what power is negative 125, maybe you're thinking, oh hey, 5 cubed is 125. Also, I just need to make it negative somehow. But that's the thing. Raising something to a power does not make it negative. We've said a negative exponent turns things into a fraction. That doesn't give us a negative. And 1 over 125 and negative 125 are not the same thing. There is no way for us to get negative 125 here. This actually is undefined or no solution or impossible, whatever it is your teacher might prefer that you say. You can't do it. If you were to type this even into your magical calculator, it will give you an error because you just can't take logarithms of negative numbers. It's not a thing you can do. Alright, this is going to start a series of 8 problems that are all titled Solve Each Equation. And there are going to be kind of a variety of ways that we might choose to go about each problem. They're not all going to be exactly the same. And so if you didn't actually do your homework on this section already, then you might be a little lost as to how do I know which way to do things. So I'll try my best here to clue you into how I know how to start the problem, but this is one of those cases where having practice is really, really helpful. So on 15, this is actually an easy one, because if there is a single logarithm on each side with the same base for each, which these are both common logarithms since they don't have a base listed, they are a base of 10. That is not necessary information on this problem, but I just thought I'd throw it in there. Since they both have a log, then the inside of their logarithms equal each other, because log of 2m equals log of 3m minus 8 means that 2m better equal 3m minus 8. If it helps you to think of it like you're canceling out the logarithms, that's fine, but it's not like we're not dividing by log on each side to make them go away. That's not how this works. We're just saying in order for these two things to be equal, the insides of them have to be equal. Kind of like if you have square root of something equals square root of something else. Well, those two things better actually be the same thing, or it doesn't make any sense to have them both have a square root symbol. This is a simple equation to solve because we want to get the m's on one side and the numbers on the other. So negative m equals negative 8, and then we divide both sides, or multiply both sides by a negative 1, so that m equals positive 8. There is a danger with logarithms of getting extraneous solutions. Extraneous solutions are solutions that occur by doing correct mathematical practices, but that should not have really been should not actually appear as a solution at all. They're not actually solutions. and they just, because we have a flawed method basically that we're using, we can get extra solutions that shouldn't really be there. That should only occur if you are using one of those properties of logarithms that we talked about earlier. So if you condense or expand, you need to check that your answer is for real or like legit. Here on 15, I can pretty quickly say, well, 2 times 8 is 16. 3 times 8 minus 8 is also 16. I'm allowed to take log of 16. That's a thing I can do even if I don't want to because I don't know what it is. But 8 should really actually be the answer here. What would not be good is if we got something and then we went and plugged it back in, we actually ended up getting a negative number inside our logarithm. That would be bad because you cannot take the logarithm of a negative number or even of 0. So yeah, that's a thing. Number 16, I only have a single logarithm, so I am going to try to rewrite this without the logarithm. That's my go-to. If you have a single logarithm, try to write it as an exponential equation. If you have an exponential equation, then chances are we might try to think of it as a logarithm and see if that helps. So before I rewrite it though, this 4 in front, I actually can just divide both sides by 4 to get rid of. So log base 3 of 3x equals 0. That 4 really did not matter to us very much at all. Now, when I say rewrite a logarithm, I'm talking about that fancy circular thing we do where we say that the base of our logarithm 3 is the base of our exponential equation. We move over to the right side to grab the right side, which is our exponent. Then we come back and take what is inside the logarithm, and that becomes our right-hand side. And then we solve this equation instead, which should be easy peasy. 3 to the 0 power is 1. And we would divide both sides by 3 and get that x equals 1/3. If we wanted to double check, which it's such a good idea to double check your answers when you are taking a test. 3 times 1/3 is 1. Log base 3 of 1. 3 to what power is 1? That's 0. And then 4 times 0 is 0. So yes, 1/3 is the correct answer. 17 is actually pretty similar to 16 because, again, we have a single logarithm and the x is inside the logarithm, so our goal is going to be to try to rewrite it in exponential form, but we do have something in front of our logarithm that we are going to want to move to the other side. So that means that we'll have log. I apparently keep trying to forget about the O in log. Log base 11 x plus 1 equals -6 divided by -6 is a positive 1. Now we're going to do that fancy smancy change to exponential form, starting with our base, which is 11. Then we move over here and grab our first power, and that equals the inside of our logarithm, which is x plus 1. So 11 to the first power, oh, I didn't want to write that. 11 to the first power is 11. So then we need to subtract 1, 10 equals x. Let's see, 10 plus 1 is 11, log base 11, 11 is 1, negative 6 times 1 is -6, so the answer. Now, here is actually where we might start running into problems, but it's not a for sure thing. Maybe we will, maybe we won't. We have 3 logarithms here. It would be nice if we had a single logarithm on the left and a single logarithm on the right, and we could do what we did on the first one. This minus sign, though, means that we can condense this into a single logarithm on the left. Since it's a minus, that means that x plus 8 will be on top, and the 2 will be on bottom. You might be thinking, well, how is that helpful? Now I have a single logarithm on each side, which means I can drop the logarithms and just say that what I really want to know is what makes x plus 8 over 2 equal 14. Now we've got an equation we can solve. We might not like it because there's a fraction, but that's simple. We can just, not that it's simple as in if you didn't think of it, you're not smart, just there's an easy way to get rid of this fraction, multiplying by 2. So 14 times 2 is 28, minus 8, minus 8. If you haven't already noticed as you're sitting in your, pre-calculus class, or maybe you're in Algebra 2 and you stumbled across this, sometimes the hardest math is the stuff you learned 5 or 6 years ago, like multiplication tables or subtracting numbers or solving equations that have fractions. So we've all been there. We've all been there. All right, so a check here, 20 plus 8 is 28. Really just, I'm telling you, what matters is that we're not getting a negative in there. The thing that you want to watch out for is if you take what you got and you plug it back in. I mean, if it doesn't make any sense, what you got, then obviously that's a bad thing. But if it gives you a negative, that is a big red flag that something went wrong. So, all right, this one is also going to require we condense. You might be thinking, well, couldn't I just move one log onto the other side? Then I've got a log on each side. But then we'd have this 2 hanging out outside of a logarithm. That is not actually a good thing. We wouldn't be able to put that 2 in a place that actually works out mathematically well. So instead, let's go ahead and condense this. We've got a minus sign, so we should rewrite this as log of 4 over negative x. And you might be thinking, well, it can't be negative x, can it? Because logarithms can't be negative, but that means that the numbers we can plug in for x, the numbers that might work, are negative numbers this time instead of them being positive numbers. It's kind of weird, but getting a no solution on one of these should actually be something that happens kind of later on, not right here where your x is. Like, that being negative is not an issue. It would have to be something later on. Maybe that will happen to us, but probably not here. It's not super likely that you'll get a no solution. Okay, so the base of this logarithm is 10 because it's not written down. So we're going to start with our base, which is 10, come around to grab our exponent, which is 2, and that equals this right here, 4 divided by negative x. So 100 equals 4 over negative x. You could think of this like cross multiplication, or just multiplying each side by a negative x to make them not be fractions. And then we're going to divide by negative 100 on both sides. So x equals, let's simplify this to negative 1 over 25. So that's what I was saying, like, if I put negative 1 over 25 in here, it changes to a positive 1 over 25. So that's okay. You can take log of positive 1 over 25. And then really if you're checking this, like, yes, you want to check to make sure that it really works out when you plug it back into the first line, but then you might need to actually go to the next line to make sure that it makes sense. Because I don't know what log base 10 of 4 is or log base 10 of 1 over 25 is, but if I put negative 1 over 25 here, I get positive 1 over 25, I multiply by the reciprocal, and that turns into a 100. So then I can actually see this through and verify that it's correct. That's kind of a complicated thing to do. So, just trust yourself. I'm sure you did it right the first time. Yeah. Okay, so we're going to use, on number 20, this cool property of exponents from back in Algebra 1, where if you have x squared times x to the 5th, you can combine those into x to the 7th using the power of addition on your exponents. Here we've got a base of 3 and a base of 3. We've got different exponents, but we can combine them into one by adding them together. That's helpful because now instead of having 2 things with exponents, I have a single thing with an exponent, which means that I can rewrite this as a logarithm with a base of 3. So we start with 3, and we go around here and grab the 1, and then we come around here and put the exponent on the right hand side. It's the exact opposite of how I was rewriting the logarithms into exponents. So hopefully that's not where you're getting tripped up. Now either I will need to be able to figure out log base 3 of 1, or I'll be able to use a calculator on my test, or my teacher just wants me to leave it in terms of logarithms. So log base 3 of 1 I do actually know, because 3 to the 0 power is 1. So that's 0. And then we would subtract 4 and divide by 2. And our answer is k. K equals -2. So if you wanted to check this, you'd say 3 to the 4th times 3 to the 2 times -2 equals 1. So that's 3 to the 4th times 3 to the -4th. And that might be where you're like, oh, I don't want to do this. But if you know the properties of exponents, then you know that you can combine those and get 3 to the 0, which does in fact equal 1. So not so bad if you remember those exponent rules. Alright, last two. I have a feeling, but it's just a feeling, that these may not work out so nicely, which means either we'll be able to use our calculator, or we're just supposed to leave them in terms of logarithms, and we'll talk about both of those things. So first step is to get the exponential part by itself. The 17 to the -3x, we need it by itself, so we add the 3 to both sides. So 17 to the -3x equals 79. So let's rewrite that as a logarithm with a base of 17. The next thing that we write after the base is the 79, and that equals our exponent, which is -3x. I don't think that there's a nice connection between 17 and 79. 17 to what power is 79? I don't know. So one thing to do is just keep working without actually knowing what it is. So we could write our answer as log base 17 of 79 over -3. You can put the negative in front or just leave it on the bottom. This is an answer. We also can plug it into our calculator if we're allowed to, or if we're asked to, and get a decimal. And I'll do that after 22 because I think it's going to be a decimal as well. So +8 + 8, 7 to the n equals 96. Rewrite that as a logarithm. Log base 7 of 96 equals n. Yeah, this definitely doesn't feel like problems that you'll be required to use a calculator on. I could be wrong. It happens more often than you might think. If we are using our calculator, and you don't get to use Desmos, sadly, you use like a TI or scientific calculator or something. Just make sure you know how to put in logarithms. It's kind of a big deal if you're allowed to use it on your test. If not, then I guess it's not a big deal, actually. Okay. Can I copy, paste? Oh, sort of. I don't know what those dollar signs are for, but this is the answer I get for log base 17 of 79 divided by -3. And then I need to do 7 and 96. And this is the answer I get for log base 7 of 96. So, probably not necessary to go all the way to the decimal, and if it is, like one way you can tell, let's say that you are allowed to use your calculator, but you're not sure if your teacher wants you to use it or not. Technically they should be smart enough to specify with or without a calculator, but there's also this cool thing where they might say round to the nearest thousandths place if necessary. That implies that you should put it in the calculator so you can round to the nearest thousandths place. Unlike with long division, it's not like you can round logarithms to the nearest thousandths place unless you know what it is as a fraction and then we're converting it to a decimal. Never mind, that doesn't even make sense. So probably just okay to leave them as logarithms. Thanks so much for watching this video. I hope it was helpful to you. I hope you ace your test. I hope you understand things a lot better than you did before, and I hope you give me a like and a subscribe and maybe even a comment to let me know how things are going or how they went. You can do it. I believe in you. You're awesome, and thanks for watching.